recording going? Nothing? You guys just want to be quiet? Listen to other people?
Well, I pretty much got to the part where you were putting a heap into a vector, and you're doing the 2 times I plus 1
Oh, yeah.
thing.
Sure.
Yeah. And from what I can see here, it looks like it might overwrite itself at some point. I'm not 100% sure.
Let's do some examples. Let me just make a new slide really quick. Yeah, because that's a important aspect of this. I'm gonna grab really quick. I'm just gonna go grab the equations just so we can reference them. Right about here. There we go. All right. So the question, the thing we should investigate is using these equations for the child of I being 2 times 1 plus 1, and then 2 times I plus 2, and the parent of I being I minus 1 divided by 2, which are two like absolutely critical equations for how this mapping is going to work. Let's test out and see if that actually works. So let's make an array. Now, array's got to be pretty big because, well, we can have a lot of stuff in it, right? Like the whole idea is that it's going to break over a long time. So let me, oh, come on. Let me insert. Let's do that again. All right, now, as we're talking, I'm going to get this set up. So remember that the whole idea behind this process is that we can get the efficiency of a tree, but we're going to do it in a non-tree-like structure because, as you'll find out with part 1 of your project, trees are great, but also coding trees are kind of finicky. They're cumbersome, right? They're not quite as intuitive and easy as we'd like them to be. But from the performance standpoint, they're really good. I'm just putting in here indices so we can work off those indices. 18, cool. Another nice thing is, depending on the application, this whole vectorized heap solution just on a vector will work just as well as doing it on a DQ, and it will definitely work better than doing it on a list. So in terms of the adaptiveness of our setup here, we're going to want to be doing this for a vector or for a DQ. We're never going to insert anything above the root, and so that means that we don't really need to worry about doing a push front. We're only ever going to do push backs, so we should be okay. All right, so we'll for this example, we'll move our arrays up to the top, and let's make some trees really quick. Just copy and paste my tree nodes. I'm going to make these a little bit smaller just because we're going to run out of room if we don't. All right.
So a heap is a wrapper for a vector or DQ.
A heap is. This is where it gets a little fuzzy. A heap is a class that is going to contain a vector or a DQ. I don't know if I'd necessarily call it a wrapper.
Oh, okay.
A wrapper implies that it's using the exact same functionality of a heap or a DQ. The problem there is that it's using a heap or a DQ for its functionality. I don't know if that makes sense or if that's clear.
Well, I'm just trying to think of like when we use stack and like that implements
Yeah.
DQ.
And that's why I want to be a little careful in that it's kind of like an adaptive container. It's not entirely like an adaptive container. It's subtly the analogy kind of holds, but it's not quite the same. Yeah, that's fine. It'll work. All right, here we go. Got to make some links. Well, while I'm doing this, any other questions before we get into how we do this whole heap mapping business? Uh-oh, this is where it gets messy. I wish the PowerPoint just natively allowed you to make trees without having to do this whole construction process. That'd be very helpful. All right. Especially that last row isn't that pretty, but it will work for what we need it to. All right, so we got 0, 1, 2. I see that question. We'll come back to it really quick. All right, so we got 3. We got 4. Come on, PowerPoint. You can do it. Nope. Oh, boo. Fitting square text boxes in a circle, you would think. Ooh, those are real small. Well, it is what it is. All right. So, right, the idea that we're going for here is that we want to check to make sure that we can use these equations and that we're not going to overwrite ourselves unintentionally, right? I want to actually prove that we can do this. That's why I went to an extra couple of steps than what I did in the lecture. So really quick, let's just do the example of going from, right, traversing from 0 to 1 to 3 to 7. So this is going to be taking the left link between the parent to the child. So our parent is going to be here, right? So I'm just going to put 0 here. Now, the children of 0 are going to be 0 times 2, which is 0 plus 1, and 0 plus 2. Okay, so that means this is going to be the left, and this is going to be the right sub trees of 0. So we're going to go down the left path. So I'm going to say this is 1. All right, cool. Let's insert really quick a text box so we can actually keep track of this. Right, we're doing 0. 0 is going 0 times 2 plus 1. That's going to get us, this is a terrible choice. We'll do 0. There we go. Gives us 1. And now that we're at 1, we're going to do 1 times 2 plus 1. That's going to give us 4 plus 1 is going to be 5. Oh, wait, what happened? What did I do wrong? That's not right. Oh, that's because that's not 5. 1 times 2 is in fact 2, not 4. And then 2 plus 1 gives me 3. There we go. That gets us to 3. So that's going to be 3. Now, really quick, 1's children are going to be 3 and 4. So now we're going to go to 3's children. So 3's children, we've got 3 times 2 plus 1. So 3 times 2 is going to give us 6 plus 1 gets us to 7, gets us there. All right, so do you kind of believe me now? Do me keep going?
I'm just a little bit confused because the indices and the data inside are like kind of the same numbers, so it's kind of
Yeah. So why don't we do this? I stop at 14, but let's try just like what is the parent of 18, right? Because that's something that I haven't necessarily. I don't have
so this
anything.
is
So what I want to do is I want to find parent of 18.
so index 18.
Well, yeah, it's a good point. So I want to find parent of the node in which his index is 18. Yeah. So
Okay.
right now I haven't actually filled in the data. The only reason I put 0, 1, and 0, 1, 3, and 7 is to show you where I was moving. You're absolutely right that these are labels, these aren't data. And I get why that's a little bit confusing because I've been putting the data inside of the nodes, and now when I got here, I've all of a sudden changed it to be the indices. So I get that. So we're at the indice 18. I want to find the parent of the indice of 18. So that's going to use this I minus 1. So 18 minus 1. So we got 17. And then what is 17 divided by 2? That's going to be 16 divided by 2. So that's 8. Okay. So that means the parent of 18 is going to be 8. So if I'm looking, let's just shade that really quick. If we're looking at that cell, we're looking for that cell's parent. That's going to be here at 8. Now let's check really quick, right? If this is 14, 15 and 16 are off of 17, 17 and 18 are off of 8. So that seems to line up pretty well.
Hmm.
Are you still not convinced? Do you want me to keep going?
I'm just like not 100% sure just how this works. I haven't looked through the entire video
Okay,
yet, so
that's
that probably
that's
doesn't help.
that's fair.
So
Does anyone else want me to keep going in this example? Right? I don't mind doing it. I just want to make sure that it's helpful. Okay, cool. Well, Zach, let me know if you run into issues and you want me to give a more detailed description of kind of what's going on here. It's something that it seems weird, and I know it seems weird, but once you go to do the priority queue, which is the homework we're going to do or the project we're going to do, um, if you rely on these two equations, that the parent of something is, or sorry, that the children of something is going to be 2 times I plus 1 and 2 times I plus 2, and that the parent is going to be I minus 1 divided by 2. If you lean into those two behaviors, it works pretty well, right? Make sure that you understand the algorithm. Make sure that you understand how you're going to use those two things. But if you just lean into those equations, they work out pretty well. All right, so we can come back to this. I want to switch gears really quick. So, question being, I have a question about the first part of the project. What happens when we insert a value that's already in the tree, or can we do that? Good. This is a question that's come up a couple times. So let me make a new slide really quick. All right, so I'm gonna copy my obscure tree structure. I'm gonna delete most of them. So what we're looking at specifically is the case in which we want to add something to a tree, but there's already that element in the tree, which is a really good question, and it's something I didn't really cover in the lecture at all. So I'm happy to dive into it now. Now, really quick, I'm shifting gears. I'm shifting notation. Is this a binary search tree as we know it should be? Yes or no?
yeah,
It is? You sure?
there's 0 or 2 elements in it.
Oh, so that's a binary tree, but for a search tree, right, the left is going to
Ah,
be smaller than our node, our right is going to be larger. So, really quick, let's just
wait a
oh, oh,
second.
rolling back, yeah.
So we're going from labels to data now?
Yes, yes, yes. That's what I meant by I'm switching
Oh,
gears right now.
sorry.
No, 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 it's okay. I need a random number generator. Here we go. Uh can I give me a dice roll? Google, you give me a dice roller. Ooh, hey, cool, nice. That's exactly what I wanted. Google, thank you. Let's do an 8-sided die. So we got 5. Roll it again. No, what? Oh man, Google, this is totally overproduced, but I love it. We got an 8. Can we put a bunch in there? Oh, we can. Nice. 4 and 5. And let's go for 3 more. All right, we've got 1, 2, and 5. 1, 2, and 5. All right, so this is definitely going to hit the question of we need to see what happens. Woo! We need to see what happens when we add a duplicate, right? Because when we add this second 4, it's going to be an issue. So the very first thing we add is a 5. So that's going to set our root to be 5. Cool, nice, no problems there. The next thing we're going to do is we're going to insert a 4. So we're going to look at the root and we're going to say, okay, is 4 less than or greater than 5? Well, 4 is less than, so that means that we can take this 4 and put it off to the side of 5, right? 4 is less than 5. All right, is 8 greater than or less than 5? 8 is greater than, so we're going to put 8 off to the side. Now remember, this is a binary search tree. I should put a label here. Search tree. This is a binary search tree, so the right branch of every node is going to be larger. The subtree will be larger than the node itself, and the left branches are going to be less than. Now we need to make a choice really quick, and I'm going to make a choice that says that if equal, we're going to go left. Now that's a kind of arbitrary choice, but we need to make sure that that's always true, and we'll see why in a moment. So I'm going to say if it's equal, we're going to go left. So if I go to add another 4, is 4 less than or equal to 5? Well, the answer is it's less than. Okay, so we get to this 4 and we say, okay, is 4 less than or greater than 4? And it turns out it's equal, so we're going to go left. So I'm going to put this new 4 to the left of my existing 4. Okay, let's keep going for a sec. 5. Is 5 less than or equal to 5? Well, it's equal, so we need to go left. So we're going to go down this left branch. Now, at this point, we can ignore anything above our 4, right? We've recursively stepped into this subtree. So I don't actually know 4, this node, does not know that the node above it is a 5. All it knows is that it is smaller than the thing above it. So we get to 4 and we say, okay, is 5 less than or greater than 4? Well, we know that it's greater than, so I'm going to put the 5 down here. All right, let me make that branch. Okay, let's keep going. 1. 1, we're going to enter the root. Is 1 less than 5? Yes. Is 1 less than 4? Yes. Is 1 less than 4? Yes. So we're going to put this 1 down here. I guess I don't need all of these anymore. We can get rid of those. All right. Next one, 2. Is 2 less than 5? Yes. Is 2 less than 4? Yes. Is 2 less than 4? Yes. Is 2 less than 1? No. Oh, this should be a 2. Sorry. Is 2 greater than 1? Yes. So it's going to go off to the side of 1. Okay, now we need to do, nope, we need to grab a node. We need to go up here and we're going to add a 5. Is 5 less than 5? No. Is 5 greater than 5? No, but 5 is equal to 5, so we're going to go left. Is 5 greater or less than 4? It's greater, so it's going to go right. Is 5 greater than 5? No. Is 5 less than or equal to 5? Yes, so it's going to go left. Now, to be fair, this doesn't necessarily prove to us that it's going to work. All we've really done is we've inserted some things and it turned out okay, right? We can imagine that if we keep adding duplicates that we're still going to be okay. But the next thing we should do is we should start removing things. But before we go there, are we okay with this? Can I keep going? Unless someone speaks up quickly, I'm going to keep trudging forward. All right, cool. So now what we want to do is we want to test that our binary search tree, with the assumption that we can go left, will still work when we remove things as well. So, well, Google, let's just keep going. Let's, oh no, not last pass, go away. All right, we want to roll our dice. Let's see if we remove a 1. Great. So now we want to remove a 1. So I'm just going to put here, remove 1. Okay, so to find a 1, we're going to look at this first node, and we're going to say, okay, is 1 less than or equal to 5? Well, we know that 1 is less than 5, so we go to 4. Is 1 less than or equal to 4? Well, we know it's less than, so we go to 4. Is 1 less than or equal to 4? Great, we go to 1. All right, once we get to 1, this is where things get a little tricky. And this is tricky regardless of the whole duplicate problem. What we need to do is we need to remove this 1 node. Now, what do we know about all of the nodes that are to the left of 1? We know that it's less than 1. And what do we know about all of the nodes to the right of 1? We know that they're greater than 1, but we also know that they are less than 4. So I'm going to do a quick switch, and it turns out that in this case it makes sense. We're going to keep doing some examples to show that it works in all cases. I'm going to take 1 and remove it, and then take the pointer of its previous parent, and I'm going to have that point to its left child. Now, if you're paying close attention, I didn't describe what I'm going to do for the right child of 1. We'll get that in a sec, right? But for right now, I can remove this 1. We're okay. Our binary search tree is still a binary search tree. It hasn't broken the set. Now, let's do the more complicated remove. Let's now remove a 4, right? Removing 4 is going to be a little more tricky. So we go to 5. We need to find the 4. Is 4 less than 5? Yes, it is. We get to this 4. Okay. We have a couple options here. We can either promote its left child or we can promote its right child. Now, the reason we can do that, again, is because anything that is to the left of 4 and anything to the right of 4 is going to be less than, or in this case, equal to its parent. So we're going to be okay if we promote either of these two up. But the problem is, if I remove this 4, so let's delete all these branches. If I remove this 4 and I take the branch for my 5 and let's say I reassign it to the right child of my 4, so I'm going to be pointing that, this begs the question, well, hold up, where do I put this remaining subtree? Well, we could pop every element out of it and then re-add it to our new tree, or we could go to that new child and we could find its lowest left node and then attach it to the 4. Now, again, let's do that algorithm really quick. This is just one of the many algorithms we can use to do this. I need to remove the 4. So to do that, I'm going to take the parent pointer's left branch and set that to the 4's right branch. Then I'm going to take the 4's right branch left branch and set that to its right's farthest left branch. And then we can delete the 4. Now, this is a pretty ugly binary search tree, but it is still, in fact, a binary search tree. It's definitely not balanced, but it is technically still a binary search tree. Everything to the left of this middle node is going to be less than it or equal in our case. And everything to the right of every node is going to be greater than. So it checks out, it works. Yeah. Does that answer the question that was posed? I can keep going too if you guys want me to, and I can reassemble the tree into a more interesting tree. Are we okay with that? Cool, right on. All right. Other questions on the binary search tree part of the project, Project 5, Part 1.
Continuing Sean's question on the insert.
Yeah.
So if I was going to be removing, if I was going to be removing, so let's say I was going to be removing 4, but 4 had 2 subnodes,
Yeah.
or 2 channels, I guess. What do we do with that?
So like the current example, or do you want me to make a new different example?
Current example works.
Yeah, cool. I'm just going to add a subnode here. Now we're a little bound in the sense that we have to make sure that the subnode here has to be greater than 4 and less than 5. So that means this is going to have to be a 5, which is a little bit weird. Now I'm going to change some stuff really quick to make it more interesting. So I'm going to make this a 6 or a 7. I'll make that a 5. I'm just going to remove this node altogether. Yeah, I'll make that a 6. Now that that's a 6, it's going to be a little more interesting for what we're going to do. Come on. This is still binary search tree, right? Everything to the left of 7 is less than it. Everything to the left of 6 is less than it. Everything to the right of 4 is greater than it. Okay, so we're still good. All right, and we want to remove the 4, correct?
Yeah.
This is still getting at your question, right?
Yeah.
Okay, cool. So we're looking for 4. We step through, we eventually find it. That's not the hard part. What we want to do is we essentially have 2 options if we remove this 4. let's break these links really quick. We can either promote the 2 or the 5. And it turns out that both of these are still binary search trees. So let's look at the 2. We promote the 2 up. We then connect this. We then connect this, right? Is that a binary search tree? Yes, right? And the reason it is because everything to the left of 6, 2 and 5, are less than 6. And then the 2, anything to its right, is greater than 2, which is 5. So this is still a binary search tree. This is still just fine. All right, if we do the other thing, where we promote the 5, there we go. This is also still a binary search tree, right?
Yeah.
So the thing that gets complicated, though, is what happens when we go to promote something and it has children, right? So let's go back to our original case. We've got these 2 and these 5s. All right, and we need to add some more. So I want to add, we'll just go all the way. We're going to add a 3 here. We got a 1. Okay. Oh, we should probably put things off of 5 too. We can keep going. We're gonna make this let's make it a 7. That means we'll make this a 10. Oh, not 10. We can't do double digits. Make that a 9. I know I just said we can't do double digits. Well, you know what? It actually doesn't matter. All right, so we got 4, 7. We need to give 7 some children. So we can put here 8 and 6. All right, so remember that the definition of our binary search tree is recursive, which means that all we really need to look at is the subtrees, and then we can go from there. So if we look at this subtree of 7 with a child of 6 and 8, that is a binary search tree. That's correct, right? The thing to the right of 7 is greater than it, and the thing to the left of 7 is less than it. And we look at this subtree over here, which is 1, 2, and 3. 1 is less than 2, so it's on the left. 3 is greater than 2, so it's on the right. Those two subtrees check out. Now let's look at the 4. Is everything to the left of the 4 less than it? Yes, right? That pans out. And then the same thing is anything to the right of 4 greater than it. And that's also yes, right? 6, 7, and 8 are all greater than 4. 4 is less than 9, and it turns out so is everything else, right, in all of these subtrees. All right, so now let's look at what happens when we remove 4, right? Because that's kind of the crux of this problem right here. We're going to break the link from 9. We need to now have 9 pointing at somewhere else. So we've removed the 4. We can go either way. And it turns out that in this example, there might be an optimal way, but in your example, it's going to have to be a generic algorithm. So which way do you want to go, left or right?
Go right.
Let's go right. So we're going to promote the 7. So that means the 9 is going to go to the right child of 4. Now, again, it doesn't matter which side the 9 goes to because we know that everything to 9's left is lower than it. So, right, it doesn't matter if there's a whole bunch more trees underneath of either of these. It doesn't matter because we already know that everything beneath it on the left is lower than it. So that means it can point to anything, right? The structure will change and the structure will be different. But from the rule of can 9 point to anything in this subtree, the answer is yes. So we've got 9 pointing at that right node. The kind of problem that we're at right now is that we've got to deal with, well, what do we do with 4's children? There, 4's left children. We need to put them somewhere, and we can't just put them as another node off of 9, right? That doesn't work. That's kind of what the 4 would be, and we can't have them hang off of the child of 7 because 7 can only have 2. So what we can do instead is we can take 4's subchildren, left subchildren, and we can instead put them on 7's leftmost subchild's left. Right? So again, everything to the left of 7 will be less than it. Everything less than this is going to be less than all of 7's left things. So we can take this and put it on 6's left child, and we go back to having a satisfactorily set binary search tree. I know that algorithm seems sloppy, but it turns out that because both of those things, the traversal to 4 and the traversal to the lowest left child, both of those two things are recursive in nature, so it actually works out pretty well. Does that help?
Yeah, thank you.
No, not a problem. It's a weird algorithm, and I highly suggest that when you go to code this, when you go to make your project, fill your tree, right? That's the first thing you should do. Well, the first thing you should do is print out a tree. So figure out your print function first, because you're not going to be able to debug this without printing it. So get it to the point where you can print out its contents. Then make sure that your insert works for all cases, right? Make sure that you can insert basically into any of the positions on your tree. Once you have your print and your insert working, then, right, start going through your removals, but do your removals by hand first, right? Figure out, okay, I need to remove the 4, so I'm going to move this thing here, I'm going to move this thing here, and then start to work up from there. There's a lot of kind of weird edge cases, and those weird edge cases are very hard to just kind of code out, right? Just to kind of start modifying your code. It just doesn't work that well to do that. And that has to do with the complexity of the recursion. It's going to be a lot easier if you do it by hand and just figure out, similar to how you figured out like an insertion into a linked list, you had a very specific process you had to go through of like, okay, go to lists next previous and reset that somewhere else, right? The same thing. You're going to have to do all of that, but for the tree. So I just suggest do it by hand, do it slow, right? Start slow and then build up, because it's going to be really hard to debug if you haven't gone slow building it up. But it's not too complex, right? It's actually a lot simpler than you think it might be in terms of how you need to move this. Because remember, I'm not enforcing a balanced tree. This tree that I'm showing you here, this is far from balanced, right? 9 has no right children and it has 6 subchildren. So this is very much not balanced. I'm not forcing you to do it balanced. Balancing is a totally different algorithm, totally separate from the removal algorithm. Cool. Okay. Other questions on the tree part of the project? Binary search tree. Nothing? Cool. Yeah. By the way, if you want, you can talk now. I just muted you because you had some weird sound going on in the background.
Okay, sorry about that.
No, that's right. You're good. We can hear you now.
On the subject of balanced trees, if we're doing the extra credit for the balanced tree,
Yeah.
and we're given a tree that cannot be a balanced binary search tree. So, like if you had, if the tree was just 3 threes, that you can't make a balanced binary search tree out of that.
Oh, that's a good point. Yeah, you good. Yeah, you're right. You can't. Okay, I accept that premise. Yeah.
What should we just not have a balance and that'll be okay?
Yeah, basically.
Or,
okay. The shorter answer to your question, well, the problem in your question is that we have to make this assumption of we always go left if it's equal to. There are ways that you can make it so you go either way. It just complicates everything more, and I don't necessarily want to introduce that complication. And the complication comes into when you go to remove something. Well, is that true? Wait, I'm thinking about this now. Can you go both ways? Always? You might be able to just go both ways always, even though I just said you have to pick one and choose it. Let's think that let's figure it out really quick, right? Let's go back to our original set, and now let's pick the way in which will make it the most balanced, even though algorithmically that doesn't really make sense. So we're gonna insert the 4 goes here. Oh, I got rid of my arrows. Come on, arrow. We insert an 8. That means the 8 is gonna go over here. We got another 4. Nope, that's not a 4. So at this point, when we go to put in a 4, we're still balanced. We're still good, right? Now, in this context, I'm going to go to the left again, but we'll see in a moment that that won't matter when we insert the third 5. Or not that it won't matter, but that we'll still test the question that Ethan's posing. All right, we're going to insert the 5. So I just said we're going to insert the 5 in a way that makes this balanced. Yeah, we can still put it here. That's still balanced, yep. Okay, let's put in the 1. This is going to be where the balance gets tricky. We got to do some rotations. There's a 1 here. We drop the 1, we drop the 1, we drop it here. Sorry, I should label that first. All right, so now we are at an unbalanced or an imbalanced tree, right? This 5 has a subtree that has a depth of 3, and it has a subtree that has a depth of 2. Now, one way that we could balance this is going to be, right, this is, man, I haven't thought about the rotational algorithms in a little bit. We want to rotate this tree and then rotate this tree. So I think what's going to happen is we need to have the 4 be our main node, and then take these 5 and the 8. And we actually, in this case, to make it balanced, we have to break that up. Now let's think about this as this balanced. That's got a height of 2 on both sides, height of 1 and 0, height of 1. Yeah, that's good. Okay, so now we need to insert a 2. 2 is going to go in the most inopportune place. That's all right. So 2 is less than 4, 2 is less than 4, 2 is greater than 1. This 4 is not balanced anymore, right? This 4 has a height of 2 on its left and a height of 0 on its right. So that means we need to rotate this subtree the way we're probably going to rotate it. Yep, we're going to... Oh, it's going to take a double rotation. Man, this is why I avoided talking about rotations in lecture, because the algorithms get tricky fast. So the rotation is going to be demoting this 4, promoting this 1, and pulling this 2 down. That'll be on that side. That'll be on that side. That will be on that side. Then you have to do another rotation. Oh, that's not the right way. We need to rotate the 2 up. Yeah, so we got to promote the 2. Okay. We're getting close to the case we care about this 5. All right, so we insert the 5. Five is gonna be greater than 4. Now we want to put it in the most balanced spot. In this case, it doesn't actually matter. Yeah, we can just put it down here. I guess that doesn't answer Ethan's question because it doesn't actually get to the worst case scenario. The short answer for you, Ethan, is gonna. Oh yeah, go ahead.
I had an idea. If you wanted to edit the search algorithm. You brought up the idea of having, like, if you had a tree that was just three of the same number, and you want to be able to, if you want to be able to search such that, if you have, that when you have equal numbers, it could be on either side. What you could do is default to the left, but every time you go left, check to see if the data of the right child is equal to the data of the current
Oh, sure. So
node.
you do like a subcheck. Oh, it's not a subcheck. You just do a one single step.
Yeah. So if you were going down, like you're going down that tree, but in that bigger tree, at some point you had a five with a five as its right child,
Yeah. Well, we can just
because you just need to do that for balancing.
do that there. Yeah.
I guess the problem with that. No, okay, but basically, then you could still find things through that five.
Yeah, it gets really weird fast. What I would say
But
is,
if you're going left, then you've already detected that the item you're looking for is less than the current node, which means nothing to the right is actually going to be valuable, right?
ignoring the equalness, yes.
But if it was equal, you would have already found it.
Oh, correct. Yeah, yeah, yeah. Well, I think a kind of a compromise to this is I don't mind if you do the balanced operations, but you exclude repeat items. I'm okay if you just enforce that in your example. That's fine.
Okay.
Yeah. I mean, the balancing aspect is still a challenging problem, ignoring the idea of having duplicates. So I think it's perfectly fine to just ignore that case if you want.
One other question then
Yeah.
on the balancing thing. Does our balancing algorithm have to be O log n?
Oh, that's a good question.
'Cause
I'm gonna say no.
Okay, because my algorithm isn't O log n, so it's probably actually less effective in the long run. But it does make a balance sometimes.
What is not log n of it?
My algorithm for a cheap and dirty, a quick and dirty, always balanced tree is whenever it detects that a tree becomes unbalanced, it strips it takes all the values of the nodes from that subtree and basically just generates a new
Yeah.
balanced tree from scratch.
Yep. Okay. Yep.
Which has the potential to be rearranging more than it needs to.
Yeah, I mean, worst case, that's a ON operation, right? Because you got to reinsert. Yeah. Well, it's like half. It's like n divided by 2.
Yeah.
Yep, that's okay for right now. That's okay. The detecting that it's imbalanced and then fixing the imbalance itself is a challenging problem, and I'm okay with that.
Okay.
I'm okay with that for now. Yeah. Getting into like the optimization of balanced search trees is like its own set of problems and would be like a whole week's worth of lecture, and I just don't want to get too sidetracked in that, which is why I made it extra credit, which is why I didn't want to make it required. There's this whole algorithm between like rotating a tree and rotating a subtree, which is weird, and it works, but at the same time it just gets really confusing really quick, and so that's why I kind of put it as a more of like a footnote to this whole conversation as opposed to a requirement for this conversation. So yeah, I think you're on the right track, Ethan. I would say keep going with where you're going.
Okay.
Yeah. Cool. Other questions on Project 5? Cool. Means you guys are experts. You're all good to go. Or you're all watching Netflix on the side. Which is fine. I don't really care, actually. What else? What other stuff you guys got? Nothing. Well, cool. Okay, unless you guys got stuff. Oh, someone's typing. Let's see. Okay, yeah, we can talk separate about that. Cool. Well, if you guys don't have anything else you want to talk about, I don't mind stopping this one here. I will post this to the stream, so if people want to review back to it, and also in the future, just so you know, you can always return back to any of the lectures to see what we talked about. Cool. By the end of today, you should be getting the part 2 of the PR5 of Project 5. That's going to be implementing a priority queue using a heap. So it's a lot of that heap conversation around how do we move stuff through a vector-like object, even though we're doing tree-like behavior. Yeah. All right. Have a good rest of the day. Oh, as a heads up, we don't have class on Friday. It's Good Friday, start of the Easter celebrations. You are welcome to still reach out to me. I'm going to be working on stuff all Friday. I'm just not going to necessarily have like a formalized class session. So if you got questions on whatever, feel free to stop by. Cool. I will see you guys later. I'm going to stop this stream or the